We played around with them just a little bit. And I'm going to set up a circuit up here to show it. This is the symbol we looked at. And it's a little different than a diode. We discussed that it's a little different than a diode in that to make it conduct, first of all, we have to forward bias it, but it don't conduct until you provide it what we call a gate signal on it. So what we can do is we can actually control when this thing conducts. And this is the makeup, and this is why it's called a thyristor, because it's got three junctions in it, and that's where it gets the name. And we have several ones that fall into this category of thyristors. So when you say an SCR and a thyristor are the same, that's false. An SCR is a thyristor. So to make the thing work, what we have to do is we have to come up here and forward bias it. So this is the symbol. This is the way it's made up. And so to forward bias it, we have to make the anode positive in respect to, and that's the big thing, in respect to the cathode. So if I was to come over here and put my load, so I'm going to put a resistor right now, and put my SCR right here. And then if I make this common, then this up here would have to be positive, right? Y'all understand that? It would have to be positive. Or if I made the cathode negative, then the anode could be negative, but it's just got to be negative in respect to it. So once we forward bias this thing, I still hadn't changed this cable out, guys. I'm sorry. So what we'd have to do is here's plus, here's minus. And what would happen is right now, if that's 25 volts, this guy would be dropping 25 volts because it hadn't been turned on. Now what we have to do to turn it on, so what's happening is I've got plus 25 volts right there. Down here I got 0 volts. So this guy here's forward bias, but it hits that junction right there, and there's no P to bias that junction, right? You understand? Here's this P, but there's no N to bias that junction. So this guy here's turned off. But what happens as soon as I apply a gate, now we usually do a pulse, so I apply a gate pulse. Then as soon as that applies a gate pulse, this goes positive, and all of a sudden we have current from gate, we have current from the cathode up through the gate. Very, very small current though, it's a gate current. Well, what that does, it basically takes this point, this 0, and comes up there and puts a 0.7 there. Well, here's 25, here's 0.7 because it's been turned on. Now all of a sudden this junction is forward biased and the SCR starts conducting. Now I come up here and take the gate away, what's going to happen? It's going to stay on because now it's in full conduction, right? You understand? So once you turn an SCR on, there's only one way you can turn it off. And that's to drop it below what we call its holding current. So we have to drop it below a holding current. So this is one of the SCRs that I have up here. One of the things we'll look at in our data sheets is, so the one I'm going to hook up for y'all is I'm going to hook up this guy right here. And it's rated at trigger current. Let's see what you call it. That peak surge current. We're not going to need that. What we're looking for is a holder current. So that means to turn this thing off, I got to drop it down below what? 3 milliamps. 3 milliamps. And then it says when it's forward biased, remember you got 2 p-in junctions, even though they're doped and they don't drop exactly 7/10. This guy, when it's in, I'm sorry, that's not the time. Whole current maximum on state voltage, this guy here is going to drop about 2.2 volts. Because remember, you're going through 3 junctions, right? You understand that? Are we okay? Makes sense? Some of these guys are going to get hot, but still, this will be the maximum voltage they'll ever drop. So odds are it's going to drop less than And what else I'm looking for is the current. So the RMS on state current, we can get what out of this guy? 4 amps. And it's in a TO222 case. So I don't know, this is the anode, and it's also got an anode lead. And then here would be the cathode, which we abbreviate K, and then the one on the right will be the gate. Everybody understand? And you can find the gate in the cathode. You can't find you can't, with your meter, you can't identify the anode, but you can identify the gate in the cathode because it's a P-N junction that you could forward bias. So as soon as you see a forward bias junction, you know the one that the positive on is the gate, the one that your black lead on is the cathode, and the other lead's got to be what? It's got to be the anode. So you can find these, you can figure out, you can't tell if they're good until you fire them and make them work, but you can definitely identify the cathode and the gate. So see, we have a P-N junction. So I just start randomly choosing leads, kind of like we did with our bipolar transistors. And then we'll start with a positive and go to the other two leads. If we don't find anything, then we'll switch to the negative on our, and then we touch up to, and eventually we'll find the gate, right? The gate. And the one that we don't find is the anode. Now what we can do is, and we're going to use a simple circuit. I've got another circuit up here that I found that I put it in the PowerPoint, but it'll take a little more time to talk about. But right here we've got the load. So here we're using a resistor, and we got a phase control circuit. So what we got is 60 hertz AC. So this is going to be like a half-wave rectifier. So what we can do is when this goes positive and this goes negative, so coming in like this, we're going to, so this is going to work at as a half-wave rectifier. But what we're going to do is we're going to be able to control where it conducts within that range. So what we're doing is when we have our positive alternation, this would be positive in respect to that, right? You understand that? So it's got the ability to turn on. But what they're doing with this thing called a phase control, here's the gate right here. So what they did is they delayed it and fired it right there. Well, as soon as they fire it, the SCR turns on. Then you can take the gate away. You can literally cut the gate lead off because once it's on, it is on. But what happens is when my input signal falls down to here, then I have no current flow through the SCR, and the SCR cuts off because we dropped it below its holding current. Then, of course, we're going to block this one because it's a half-wave rectifier, and then it starts going positive again. But what is we haven't done what? We haven't turned the SCR on. So they're doing the same thing. Then we fire it, and then we would get an average. So I know that if this was a half-wave rectifier, what would be my average voltage for half-wave rectifiers? Voltage DC would be what? Equal to what? Equals what? Half-wave rectifiers. What's the output voltage equal to? What's the output voltage of what's the DC output? If this was a half wave, what's the formula for the DC output of a half wave rectifier? So we've been dealing with these dang things all semester long, and nobody in here knows the formula for the output of a half wave rectifier. You're close. That's full wave. Now V peak over pi for half wave. V peak over pi. So what am I going to get? Well, I'm going to get less than V peak over pi. Now, of course, we know that this is equal to 180 degrees this is equal to 180 degrees of my input signal. So what we're doing is we're firing this thing at 90 degrees. So we're going to get less than V peak over pi. Y'all understand? But what would it be? So let's look up the formula. It's going to be V peak over pi times the cosine. It's 1 minus the cosine. It's 1 minus the cosine, right? Of the firing angle. Is that it? It's down in the bottom where it says SERs. Is that the formula? 1 minus the cosine. So y'all need to get out y'all's formula. Yeah. 1 minus the cosine. So we took the cosine of 90. The cosine of 90 is equal to no, that's for full way. No, I'm sorry. The formula the formula they give you is 2V peak over pi, and then they say divided by 2, which is going to cancel those out, right? Then it says times 1 minus the cosine. Is that the formula? Yeah, well, that's what I did. I went ahead and divided by 2 to start off with. Okay. Thanks on you. So what's cosine of 90 degrees? So this is not going to work out. I need to look at that formula again. Something's wrong. Cosine of 90 degrees is 0. One plus the cosine? Well, this is still not going to work out because that's going to give us the same formula. That's going to give us the same average. I need to check that formula. No, not that formula. The cosine. I know what it is. The cosine of the sine of 90 is 1 and the cosine of 90 is 0. So what we'd end up with is we'd end up with the same formula that we did for half wave, and we can't get that much out of. I need to go back and double check that formula. Y'all understand what I'm saying? Yes or no? Yeah, there's two things that I know dealing with AC so long. We call it a sine wave, and I know the cosine and the sine are opposite of each other. So the cosine of 0 is 1, and the sine of 0 is 0. The cosine of 90 is 0, and the sine of 90 is 1. So, but the problem is, if I took the cosine of 90, and you say I add 1, it says I add 1 to it, and that's going to be 2, and that means we're going to get twice out than we put it, and then we would get for a half wave. So something's wrong with that formula. You understand what I'm saying? So that formula's wrong. Because I know I'm on, if this is V peak over pi, then this right here has got to be less than V peak over pi. Y'all understand? Yes or no? Huh? What do you mean on the formula sheet? Huh? The formula is not in the book, unfortunately. And this probably came out of Floyd's. I don't know. We're in chapter 15, by the way, guys. Yeah, which is 13? 13. Now, normally what we do, so we can use the SER. Let me exit this out. So we could do this. We could use it in a full wave bridge rectifier. But what I'll do is I'll come up here and replace these two diodes So I'll replace these two diodes down here with SCRs. And then I'll bring my AC in right here. Now what we're going to do is what we have to do is we have to understand what's going to do this gate circuit right here. Yeah, that's what it is. But see, the cosine of 90 is 1, so that's going to be 1 plus 1, which is 2 divided by 2, which is 1. And then we come up and get the same thing that we would get for half wave, and I know it's got to be less than that, right? So that's got to be the wrong formula. Yeah, so the formula that gives us 2 V peak over pi, which is for full wave, and then it says times the cosine 1 plus the cosine. So this is why I realized that formula couldn't be right. Times, right, 1 plus the cosine of the angle, and then divided by 2. Well, you got to realize if this is divided by 2, that's going to be divided by 2. So I just went ahead and did that. Well, the problem is the cosine of 90. The cosine of 90 degrees is 0. Well, that would be right. Let's try that. That is right. So that's going to be 2 V peak over pi, and this is going to be 1. It's going to be times 0.5. No, that's still going to be the same. So if this was 12.6 volts peak, then I'm going to take 12.6 divided by 3.14. That means we get about our average DC would be equal to approximately 4 volts. If I took 12.6 and then I divide that by pi, divided by 3.14, and then I multiply that by 0.5. Huh? That looks like it might be right. Because the sine of 9, your cosine is 0. This is divided by 2 over here. So this would be 1. So we would get, it looks like if we did this, if we're only using 1/2 of it, it looks like that's what we would get, is we would get 1/2 of this, right? So it looks right, guys. So I just got confused. So if you had a firing angle of 0, then this would be 1. That's plus 1 plus 1 is 2. And then that would be 2, that'd be 1, and that would give you, no, that's still, this says halfway? So a firing angle of 0, that's going to be 2 divided by 2. And then that's going to be 2 V peak over pi. So it's still, something's still wrong there. I'd have to look over there. Because of this. It looks like the half wave. So what does it say for full wave? What's the formula for full wave? Okay, I need to look at that. It looks like half wave, that should be wrong, because that's still not right. Because if I fired it right here, then we would get V peak over pi. But if that would be 1 plus 1 is 2, that's going to be 1, that's going to be 2 V peak over pi, that's full way. So I'll go back and look at that. It's not on the test, so, but I would like for y'all to have the right formula in case y'all run into these things out in the field. What you got to understand is if I can control this firing angle, then I can control my output voltage, right? You understand? If I can control my output voltage, then I can control my output current. So we use these a lot to run motors, DC motors, because the DC motor sees the average of the voltage. So if I come over here and ran a DC motor with this, then what could we do? Well, we can control the speed all the way from where? From full on to off. And we can precisely control this thing. Another way, what we're doing is I'm going to do it a little different in that instead of doing this, I'm going to fire it with one circuit. So what I've done is I've come up here on the circuit that I'm going to hook up for y'all is I've got just a full wave bridge. And I'm not going to color those diodes in. And then we're going to bring in from a transformer, we're going to bring in 12.6 volts AC. And then what I'm going to do is I'm going to come over here and we're going to put a little delay circuit in that I'm going to have to figure out. And I'm going to put a capacitor. And then we'll come over here and we're going to put our motor. Now, so I can see what's going on with my scope, is I'm going to put the SCR up here. And we'll fire it right here. And then I'm going to put my motor down in the cathode. Now, why I'm doing that is so I can look at this with an oscilloscope. If it was up in the cathode, if it was up in the anode, I couldn't, we can't put this, so this lead on our scope, is ground. You can't move ground inside a circuit, right? You understand that? So I'm going to wire the motor on the bottom. So what I'm doing is I'm getting this right here. So I've already got a half wave. And what happens is that I'm going to, when this starts going positive, the capacitor starts charging. Who's had AC? No, you hadn't had AC, had you? Okay. Charles, have you had AC? Brian, you've had AC, hadn't you? The way a capacitor works, it works like a little tiny battery. So we charge a battery. So right off, we start off, we'll have this thing charged to 0 volts. And then when we turn power on, the thing starts charging. But what we're doing is we're delaying the charge with a resistor. So what we have is on a capacitor, we have a little formula called time is equal to R times C. So this would be the size of the capacitor in farads. And the farad is basically the storage capability of the capacitor. So the bigger the capacitor, the more coulombs it can store up to. And y'all know the difference between a coulomb and an amp. So what's a coulomb? I think that was one of the terms y'all learned in DC. So what's a coulomb? A coulomb is a stored charge. A amp is a charge in motion. So a coulomb is 6.18 times 10 to the 18th electrons stored. So 1 amp is basically 1 coulomb worth of electrons, but it's in what? It's in motion. So a coulomb and an amp are kind of the same thing. So what we do, a capacitor is rated on how many coulombs it can hold. So the bigger the farads, the more electrons are or holes we could stick inside that thing, right? You understand? And it charges. The problem is it can provide a lot of energy real fast, but then it bleeds off instantly. So it doesn't constantly chemically regenerate its difference in potential. So that means if I came up here and started this thing up, I start off with a plus 25 volts. This starts off with 0. Then what happens is this thing starts charging instantly, and then it charges like this. And eventually it would get fully charged. And then when it's fully charged, all the current stops. So that's why in a DC circuit, a capacitor acts like an open. Once it's charged, it's open because there's no more DC current flow to it. But what's real neat is we can use it to block DC, and AC can go through it, which is pretty neat. But we're not going to. So what's happening is I'm delaying the charge by this. So this thing starts going positive, and then I'm delaying this charge right here so I'm delaying when this can build up to whatever the gate voltage happens to be. So what does it say? What gate voltage does it say we need on this thing? So it says to trigger it, we need about 0.8 of a volt. Well, what I'm doing is I'm delaying it. I'm allowing that capacitor to charge, right? You understand? So we delay the firing angle, and then of course what happens is we'll come over here, and even though I'm putting that right there, what my motor is going to see is it's going to see a flat spot, and then depending on where I fire it, then it's going to come over here and see the rest of the alternation. So what's going to happen is your motor is going to run at a lower speed. Now the problem is I didn't draw this quite right. I should have drawn it like this. Then we complete the alternation, and then we drop down and the SCR turns off. Then we got a little flat spot. We hold it off before we trigger it, and then we trigger the rest of the alternation. So what happens is it slows down. So we're not getting 2 VP over pi, we're getting something less than that. Everybody follow this? Now the problem with this circuit is the best I can do is 90 degrees. Because if I try to set it above 90, the capacitor's not going to charge up there, right? We're going to put too much time in there. So if we're going to use the entire cycle, we would have to use some other type of circuit. But what I wanted you to see is that these SCRs, I could control a DC motor like this. So I could come up here and use a transistor. Now what's the problem with a transistor? Well, if I have 25 volts right here, and then if I have 25 volts, and I want this motor to run at a certain speed, let's say I want it to run at 3 volts, then my transistor is going to have to drop 22 volts. And if I push current through a voltage, what does it create? If I push current through a voltage. Yeah, you're exactly right. Creates that right there, right? You understand? So that means my transistors are going to have to be extremely high powered to try to run a motor. But this guy right here, you either turn it on or off. So when it's on, it's dropping very little voltage. When it's off, there's no current flow through it, right? You understand? Just leakage current. So that means I can control a motor so this right here, this watts right here is wasted. What work is that watts being dropped across my transistor? What work is it doing? Well, it's creating heat. It's not running the motor, so the motor's getting very little power, but I'm consuming a lot of power, right? You understand? Yes or no? Over here, if this guy, when it's on, if it drops 2 volts, that's 2 volts. And that's the maximum level drop, 2.2 volts. If I'm running less than 4 amps through it, it's going to be dropping less than what? 2.2 volts. So now, if I want 3 volts across this thing, this guy, when it's on, it's going to drop 2.2 volts, and when it's off, it's going to drop the rest of it, but there's not going to be any current flow through it. So my SCR is going to be a lot efficient, so it's not hardly wasting any watts, right? You understand? So we don't run motors with with transistors very often unless we do something called pulse width modulation, which is very, very popular now, where we switch the transistors off and on, which is pretty neat. So if you get out in big industry, you're going to see, that's been around a while, you're going to see a lot of SCR drives. But somehow we got to come up with a circuit that can get past 90 degrees. If I can do that, then these things will become very efficient. And firing circuits are real hard to figure out. So this is a basic firing circuit that would work past 125 degrees. This uses a little integrated circuit called a 555. It's a really neat little IC. But this is just this would just be a circuit that will allow you. So I'm having to add more electronics to it, right? You understand, to get past 90 degrees. So if you look up an SCR firing circuit, most of them are going to show that little capacitor resistor thing. So if I go on the internet and look on the SCR firing circuit, we'll see most of them are going to show that little thing that we just looked at. Oh, by the way, notice over here, normally what we do is if we're dealing with an extremely high power circuit, and I'll go in and find some of these things, we don't want to connect our electronic circuit over to a 10,000 volt circuit. So normally what we do is we fire the SCR. Now we're not going to have that problem because our circuit, so let's say I come over here. And I lost my, I still got it somewhere now. Here. So let's say I have my electronics board right here, and it's running at 24 volts. But I'm over here and I've got my big old SCR out here. And let's say it's on 440. And then I've got it running in DC motor. I'm just going to put it back down in here again. You can put it either in the cathode or the anode. Now, what I want this 440 volts to get into my little 24 volt firing circuit. Well, what do you think it would do if something happened? It'd flat blow all my electronics up, right? Understand? So what we do is we isolate that firing, we isolate the power circuit from the firing circuit. One of the methods we use is we use a little gate transformer. In fact, it's called a pulse transformer. And what they do is they put dots on these things so you make sure you hook them up right. And then what you would do is you would take this and you would hook it up there, and you'd take this and you'd connect it there. So what happens, we know a transformer won't pass DC, but it'll pass a pulse. So when I fire it, it would pass it through there. So normally what we do is we fire these things either through an optical isolator or we fire them through a pulse transformer. You got to hook up that pulse transformer right, so they'll have polarizing dots on the pulse transformer to make sure when this goes positive over here, then it pulses positive on the other side. So what happens if something happens and this SCR shorts and puts that 600 volts right there, it's going to burn up your pulse transformer, and you replace that pulse transformer for almost nothing, but you don't mess up your your $2,000 PLC. So normally when we fire these things in a high energy circuit, we fire it through something, and then if something happens, we can also fire it through we can fire it through a optical isolator. So what they do is it's built in. It's usually got 6 pins, and then we'll have a photodiode, and then over here we either have a photo transistor or right here would have LED, and then we would fire the SCR over on this side over here, and that way if something goes wrong, you don't screw up your computer. You just screw up the little optical isolator, or that optical isolator. You screw up your pulse transformer. You know? We'd like to sacrifice a $2 part a lot faster than we want to sacrifice a $2,000 part, right? Because if you let that 600 volts or 440 get inside a PLC, it's going to do what? It's going to blow that thing up. So you'll see pulse transformers, and it allows us to, so what you'll see is these pulse transformers will be out mounted on the package with the SCR. And then they run two little wires back to your PLC, back to your control program. There'll be one red and one white wire. The red wire will be your gate. And so your pulse transformer is even out there with your SCR. But this is the circuit. The other circuit is the one I'm working. So where's my power? But you look, there's the same circuit, basically the same circuit. Here we're firing it with a UJT, which we'll get to later on. UJT is a neat little IC integrated circuit. Let's see, here's the same circuit that I just drew up there. Here's the firing circuit for the SCR. They're firing it with a guy called a UJT, which we'll talk about. And there's the gate transformer. For two SCRs, and we'll look at that. So you can fire two SCRs at the same time, but if one of them's reverse bias, it's not going to turn off, right? You understand? I mean, it's not going to turn on. You know, only the forward bias one will turn on. So these are just firing circuits, you know, and most of them are just simple firing circuit that I'm going to hook up. The only problem is with the firing circuit that we got, the maximum that we could get is 1/2. Are we okay? And so I tried to simulate this on the electronic workbench, but it won't even fire. Electronic workbench, it's got an SCR symbol, but for some reason it don't simulate. I can't fire it. Triacs are what we use in solid state SCRs. I mean solid state relays. We can't use these to control a motor. A DC motor works on current, which is proportional to the voltage. So if we vary the voltage on the DC motor, we can vary the speed. AC motors, we don't vary the voltage on them, unless it's what we call a universal motor, like you got it in a hand drill. AC motors, they try to run at 120 times the frequency divided by the number of poles. So you see there's no voltage in there. The problem with an AC motor, if you put more voltage on it, it's not going to run any faster. And if you drop the voltage down, remember voltage varies with the square. You can stall your motors just like that. So we don't run AC motors with a varying voltage. We run AC motors either by varying the number of poles, which is what you do on if you got a ceiling fan, that's what you're doing when you're clicking through those speeds, is you're changing the number of poles. The more poles you put in, the slower the motor runs. Or we can vary the frequency, but when we vary the frequency, we have to vary the voltage. But we can use triacs for all neat times. We can use them for solid state relays. What's the problem with a relay? A relay is electromechanical. And SCR is electronic. So electrode. So what does that mean? Well, a triac can only fire, so a relay can fail either what? It's like your car. Your car is an electromechanical device. It can fail electrically, or it can fail what? Mechanically. So anytime you got something that's electromechanical, it's going to fail more than something that's totally electronic. because totally electrical devices can only fail electrically. They can't fail mechanically. So we have solid state relays, and they're basically all they have is if it's an AC relay, then a solid state relay would use a triac. Now we do use triacs in light dimmer circuits. Anybody got a light dimmer circuit in their house? That's a triac. So we can use a triac. So a triac is either off or it's on, right? You understand? But a triac is kind of different, and they don't show it right here. But the way the triac is made, let me go back to my blank slide. So a triac uses the same feature. Got 3 junctions, P, N, P, N. Well, the triac has another one over here. It's really neat. There, over here it goes N, P, N, P. And then this would be the gate right here. So I will gate it right here, and then I'll gate it right here. These two are connected together, and this is called MT2. These two are connected together, and this lead is called MT1. So how do we turn this thing on? Well, this one would turn on when this is positive and this is negative. We could gate it with a positive pulse. This guy here's the other side's going to be off, right? You understand? Now on the other one, when this goes negative and this goes positive, I'll have to gate this with a what? With a negative pulse, and then it'll turn on the other alternation. So what I can do, if I fire it with a 0 degree angle, we get that. If I fire it with a less than an angle, then what we'll do is we'll get something like this. So my average, my RMS value's got to go down, right? You understand? And this is where a true RMS meter would work. All your regular meters does is your regular meters uses V peak over pi. I'm sorry. That's what your meter uses. Of course, no, it don't use that. What your meter uses, it uses that 0.707. That's only for a sine wave, right? You understand that? Well, the problem is this is not a sine wave anymore. Now, this part's so if you've got a regular meter and you look at the output of a triac, it's not going to give you the right voltage unless it's passing the entire. So, but a true RMS meter would. Now it's going to show less, but it's not going to read what you're actually getting across your load. So we can use these things on resistive loads. We can use them on heaters where I can adjust the temperature. We can use them on light dimmers. So if you got a light dimmer on your house, you can use them on that. Solid state relays. I've got lights out on my house that come on at night. They're motion detectors, but they only come on at night. How does it turn those lights on and off? Turns it on with the triac. I mean, it's a real simple circuit. You can fix a light that comes on at night. All you'd have to do is you come up and do this. So you have a resistor, and then what you do is you'll have a photo resistor, and then you just gate your. Then here we're going to look at a device called a diac, which is basically kind of like a zener. And then what you would do is you would gate your triac over here. And then your light bulb would be up in here somewhere. Let me do a little better job drawing that down. So if I was to go out there and take my circuit, if you got lights that come on at night, like all these interstate lights up here, basically the same circuit. We have to put the resistor down on the bottom because we want the voltage drop to go up when it gets dark. So this will be my photo cell down here. And then my light bulb would be right here. And then my triac would be right here. And then what I would do, this would be my neutral. And then I'm going to gate it. Now this might work, but it won't work real good. But we could come up and do this, and it would come on at night if we choose our resistors right. Normally you're going to see another device in here called a diac, which is kind of like a AC zener. So what happens? It breaks over at a certain voltage. So that's probably what you're going to see. So if you had one of these lights that come on at night, go off during the day, this is the basic circuit. So these are triacs. So anytime you see a solid state AC relay, it uses triacs. You have your lights at night. If you got motion detectors on your house at night, then it's going to use a watt to turn it on. It's going to use a triac, a solid state relay. And this is the last thing we'll look at, and we'll just take a glimpse into this, and we'll let y'all go loud. This is a device called a UJT, a unijunction transistor. So the leads on it are kind of strange. Unijunction transistors have two bases and then one emitter lead. So they're called B1 and B2. We use these in oscillator circuits. What's an oscillator? Everybody know? What does that mean? What does oscillation mean? Not rotate. Goes back and forth. So if I'm on, so this guy right here operates off of DC. So we bring it in, we bring AC, we have power supplies in it, and I think we actually showed y'all this taken apart. Got a power supply. Creates a plus and minus power supply. And then it's got oscillator circuits in it that we can control the frequency of. So what is it doing? It's taking AC, DC, and converting it back into what? AC. So anytime I have a circuit that converts DC back into AC, we have to go through what circuit? Some type of oscillator that electronically generates a frequency from DC. So if you got an inverter that you plug into, you put on your car to run power tools, it's got a watt in it. It's got an inverter. My wife has got a 120 volt 15 amp plug in her van. But what does she get off her battery? She gets DC, so she's got an oscillator in there. They usually call those things inverters. If you ever heard of inverter, that's the same. So a UJT will oscillate. So it means if I design this circuit right, I put DC on it, it's going to oscillate. So I'll get a varying a waveform out of this. Now this is not a sine wave. This is going to give us a waveform that looks like this. So it's going to pulse, turn off, pulse, turn off, pulse, turn off, but it'll do that from now to doomsday. So these guys work really, really well at firing SCRs. So we'll look at the next circuit. Initially, the capacitor is uncharged and the UJT is off. When power is applied, the capacitor charges. Once the cap charges up to the UJT threshold voltage, it's called the intrinsic standoff ratio. The UJT turns on and discharges the capacitor. As soon as the capacitor discharges, the UJT shuts off. After the discharge, the UJT's lower threshold voltage or valley voltage, the UJT turns off, allowing the capacitor to charge once again in cycles. So where's the circuit at? So this is the makeup of a UJT. So this is what gets people confused. And why they did this, guys, I have no idea. I wish they would have said we have two emitters and a base. But for some reason, when they designed this thing, we fire this with the emitter. And then we conduct through the bases. So the way this thing works is it's like this. So notice we have a P injunction. We have a P injunction right here between this and either base 1 or base 2. Are you okay? So this is the way it works right here. So we have RB1 and RB2. So what this is, we know that silicon is a semiconductor. So what we do is when I come over here, if I have a block of silicon, then it acts like nothing but we can make it act like a resistor, right? You understand? Well, what we're doing is we're bringing a lead into here, and so what that does is that sets up a voltage divider. Okay, now follow this. So what happens is as soon as I put power across this thing, let's say I put 25 volts, then we're going to distribute 25 volts across those two resistors. Does that make sense? So let's say, for the practical purposes, they're not. Let's say they're equal to each other. So let's say this is 5K and this is 5K. Then what would my voltage be right here? Yeah, we're home. We're having class in here. Jesselneer building is the building connected to this. So drive around the parking lot, and there's a building right next to this. They're right side by side. Sure. So what would my voltage be right here? Two resistors. They're the same. They got to drop the same voltage. Kirchhoff's voltage law says the sums of the resistors have to equal to the applied voltage. So what would be the voltage there relative to this lead right here? What would be that voltage right there? So they're both 5Ks. They got to drop the same voltage. They're the same value. They're in series. Current in them's the same. I got 25 volts applied to the circuit. They got to drop the same voltage. And Kirchhoff's law says all the voltage has to be dropped. Well, how would it be? What's it got to be? What's this voltage going to be? What's this resistor right here going to drop? Good, 12.5 volts. So this guy right here would be what? 12.5 volts. Okay, you understand? So right here, I've got this. So right now, I've got 25 volts right there. That means I have 12.5 volts sitting right there. What would be required on this emitter to forward bias that diode? But I got plus 25 over here. If I put 0.7 volts over there, then I've got plus 25 on the cathode. I got 0.7 on the anode. That sucker's reverse bias. My anode is not positive in respect to the cathode. So what would I have to put right here? About what? About 13.2 volts. Y'all understand that? So now it forward biases. As soon as it forward biases, we get current flow right there. RB1 basically disappears. Right? You understand that? It disappears because now we have a forward bias p-n junction. Now RB1 is not acting like a resistor. RB1 is acting like a diode, a forward bias diode. So the thing drops off. So what I would do is I would start off, my output would be there, and as soon as it fires, what's it going to do? It's going to do this. Now this guy here would sit here happy until we do something. But what we're going to do is we're going to come over here and put a resistor, and then we're going to come over here and put a capacitor. And so what happens, and these two right here are going to be connected together. So what happens when I put voltage on this thing, 25.5, 12.5 volts, this capacitor starts charging up. It's going to try to charge up to 25 volts. Well, as soon as it charges up to 13.7 volts, then this diode's forward bias and it discharges the capacitor. When it discharges the capacitor, it drops down below 13.7 volts. The UJT cuts off. We're down here. right? You understand? UJT cuts off. Depends on where I take my output off. We'll have to look at that. Then what we got to do? Then the capacitor will start doing what? It would start charging again. In fact, we usually take our output off right here. So what happens is when it fires, I get this, and then it drops down, and it fires, and it drops down, and fires, and it drops down, and fires, and it drops down. So that's what we get out of this thing. Now, how could we change the frequency? Well, if I came over here and made this variable, then I could change the output frequency. So the smaller I made it, the faster the capacitor would charge. But what happens is this thing, as long as I got 25 volts up there, what's this thing going to do? It's going to sit there and do what? It's going to just sit there and oscillate. Back and forth, 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 back and forth. Now, what it is there's a ratio between these two resistors there. Now, what we're looking at is we're looking at RB1. So we have what we call an intrinsic standoff ratio. So what we would find out, if I wanted to get the ratio of this resistor right here, it's going to be RB1 divided by RB1 plus RB2. Now, we used this before. We called it the voltage divider formula. So what that was, it gives me the ratio of this resistor to this resistor. Y'all understand? So that's what they call the intrinsic standoff ratio. So what I can do is I can multiply that stand ratio times my applied voltage, and that would tell me where this thing's going to fire at, plus 0.7. Why? So let's say it had an intrinsic standoff ratio of 0.15. Then what I would do, I say, okay, where's this thing going to fire at? Well, it's going to fire when I get at 25 times 0.15, and then up plus 0.7. And that's where it'll fire at. And why the 0.7? Because we still got to do what? So that gives me the voltage here at 25 volts. That gives me the voltage there at 25 volts. But I got a forward bias diode. So you'll see this guy fire an SCR a lot, because what it'll do, instead of me getting a gradual voltage, it literally fires the SCR. And it'll keep firing it until, as long as that voltage is up there. You got to fire an SCR at least once, but it don't hurt to multiple fire it, right? So we use that UJTs a lot to fire SCR. Okay, y'all go left. What else is in this chapter? UJTs is in this chapter, right? What else is in this chapter? That's all that's in here? UJT. You don't have diex in there? Okay, diex is really interesting. Let's go left, guys. Don't take a break and then go left. It's what? Yes. No, these are all wireless. Maybe the wireless card's not working. I wish they wouldn't have done that. Because they came in and they put the plug, but we don't have a cable. You can make cable. Hook it up and work it. You know how to make a network cable? Huh? Yeah. You do? Well, we've got everything here to make it. We teach that in the cable splicing course. Cable splicing and installation. We teach all that termination and splicing. The first 8 weeks, the first 4 weeks is metal, and the last 4 weeks is fiber optic. Oh, okay. I see. You got your laptop?
Yeah.
I did sign your laptop, didn't I?
Yeah.
Okay.
So that one.
Okay, I fixed that. Should sign that. So that's how y'all go to. Yeah, now I told y'all gonna have to use 2 power supplies. Right? You can't use the power supplies on the phone. Understand why? Power supplies on the trainer. The 2 DC power supplies on the trainer, the variable power supplies on the trainer. Ground. So there's no way in the world. So this one, both these require the negative to be connected to common. So the only one I've got is connected to common is this right here. I can't do that. So what you're going to do is you're going to have to use one of these power supplies in the lab. Okay. Now remember, you're going to have to look at the common. You can use another thing.